Hi, and welcome to the RISC-V Summit 2022. My name is Christoph Müllner, and I'd like to give you a tutorial about toolchains in the RISC-V software ecosystem. Let's have a look at our agenda. After a short intro, there will be 4 different parts. In part 1, we will talk about RISC-V International. We will have a look at the different technical groups and the specifications that they are writing. In part 2, we will have a look at RISC-V toolchains. We will discuss the terminology and have a look at the different components of toolchains. Part 3 will be a hands-on session. We will be building different RISC-V toolchains. In part 4, we will have yet another hands-on session. In this session, we will be debugging in an emulated environment. Finally, there will be a summary and some further links and references. Before we start, a few words about me. My name is Christoph Müllner. I'm based in Vienna, Austria, and I'm working at VRULL. I have multiple years of experience with compiler technologies and embedded Linux systems. At VRULL, I'm leading a team of compiler developers, and I'm also chairing the Toolchain SIG of RISC-V International. Let's have a look what this tutorial is about. Toolchains are an essential part of the software ecosystem. They provide all the tools to enable software development, such as compilers, linkers, and assemblers. Toolchains also bring the fundamental parts of the execution environment, like language runtimes for C and C++. RISC-V is a modular ISA. This brings opportunities and challenges for the software ecosystem. And toolchains are among the pieces of the software ecosystem that need to address that. In order to improve toolchains, we need to deeply understand what they are doing. This tutorial covers the fundamental concepts of RISC-V and of toolchains. It also has some hands-on sessions, and there is a lot of reference material for further information. Note that this tutorial was produced for the RISC-V Summit 2022. In part 1 of the tutorial, we will have a look at RISC-V International. We will quickly go through the history of RISC-V and RISC-V International. Then we will have a look at the structure of the technical groups. We will look at the fundamentals of the RISC-V specifications and ISA extensions. And finally, we will get an overview of toolchain-related technical groups. Okay, let's start with a brief history of RISC-V and RISC-V International. RISC-V is a free and open instruction set architecture, or ISA. It was developed at the University of California in Berkeley in 2010. The initial authors were Christoph Müllner, Andrew Waterman, Jan Subli, and David Patterson. In 2015, the RISC-V Foundation was founded to own and develop RISC-V. Later, the foundation was renamed to RISC-V International, and it became a Swiss organization. The homepage of RISC-V International is riscv.org. RISC-V International is a non-for-profit organization, and it is controlled by its members. It's recommended to become a member, and for individual contributors, there is no membership fee. RISC-V International consists of the following structural parts. There's a board of directors, there's a technical steering committee and technical groups. There is the executive team, including the CTO Mark Himmelstein, and there is the staff team. Let's have a closer look at the technical groups. The technical groups are those which are creating new ISA extensions and specifications. At the top, there is the Technical Steering Committee, or TSC. The TSC is responsible for building a strategy, addressing escalations, approval of new groups, and the final ratification of specifications. It delegates most of its responsibilities to other groups. The CTO, Mark Himmelstein, is responsible for creating a strategy, organizational areas like elections, and creating a roadmap. There are two ISA committees, or ICs, the Privileged IC and the Unprivileged IC. They are responsible for creating ISA extension TGs, driving the gap analysis, and developing a strategy for further development. There are additionally horizontal committees like the Application and Tools HC, the Privileged Software HC, the Security HC, and others. They represent important technical areas, drive the integration, do the gap analysis, and take care of a proper strategy. The specifications are written by task groups or TGs. For example, the PS ABI TG, Unified Discovery TG, or Code Size TG. A TG is a group with a well-defined scope and work product. For example, as mentioned, a specification. An important aspect here is that a TG is disbanded once it has completed its work product. So once a specification has been ratified, the TG will be shut down. Continuity is represented by special interest groups, or SIGs. There is a SIG for Toolchains, for Android, for simulators, for HPC, and many others. SIGs develop the strategies, do the gap analysis, but they don't have any active work product. As mentioned before, it's recommended to become a member. As a member, you have access to a lot of resources within RISC-V International. All committees, TGs, and SIGs have regular meetings, and all members are welcome to attend. So just feel free to listen in, or even better, actively participate and work on improving RISC-V. Group internal discussions and information exchange is handled via mailing list. There's also a wiki and GitHub repositories to store information. Additionally, RISC-V International has a code of conduct. Let's have a look at specifications. Task groups, or TGs, typically work on new specifications or new standard specifications. This might be either ISA extensions, for example, new instructions, or non-ISA extensions, which could be APIs or ABIs. The life cycle of a standard specification knows the following states. A specification is in development when it's an internal work in progress document. The specification is stable if it's an internal release, but there are no guarantees about any future changes. So you need to expect that everything in this document might be subject to change. The lifecycle state frozen means that the specification passed the architectural review and is in the 45-day public review period. Changes are very unlikely once the specification is frozen, and they are only allowed if there are truly critical issues which have been identified during the public review. Finally, a specification becomes ratified. This happens when the public review period is over, all issues which have been reported have been addressed, and the document has been approved and ratified by the TSC. Once a specification is ratified, it is very unlikely to see any future changes. Still, it is possible in order to clarify the existing text or to fix editorial bugs. So what are these ISA extensions? RISC-V has built-in customization and modularization. The goal here is to innovate in form of ISA extensions. There are two kinds of extensions: standard extensions or custom extensions, or sometimes called vendor extensions. Standard extensions are a work product of a TG of RISC-V International. Standard extensions are also ratified by RISC-V International. On the other hand, custom extensions or vendor extensions are non-standard extensions that are using the custom encoding space that is reserved for exactly that purpose. These extensions are not developed by RISC-V International. In fact, everyone can write a custom extension. There are also non-conforming extensions, which are non-standard extensions that use the standard encoding space. Of course, all standard extensions are aimed to be supported upstream in the toolchain projects. However, with non-standard extensions, there are no guarantees that this will happen. In fact, it is up to the upstream maintainers to decide which custom extension will be accepted upstream or not. Let's have a look at non-ISA extensions. I've picked 3 examples here. First of all, the RISC-V PS ABI document, the processor-specific application binary interface. This document includes the calling convention, the RISC-V specific parts of the ELF object file format, the dwarf debug information format, the code models for RISC-V, and relocation and relaxation. There's also the RISC-V vector intrinsics documentation, which is currently being written. And there is the SBI, the supervisor binary interface. RISC-V International has the following technical groups which are relevant for toolchain developers. First of all, there is the toolchain SIG, which develops strategies, identifies gaps, and prioritizes tasks for the software development environment used to build the RISC-V software ecosystem. This toolchain SIG is governed by the Application and Tools Horizontal Committee. There's also the PSABI task group, which is working on the next PSABI specification release. We have the Vector Intrinsics TG, which has just been created recently, which is writing on a documentation that standardizes the vector intrinsics of RISC-V. Besides these groups, there are also community-driven documents. For example, we have the C API, which includes extensions of the C language, for example, test macros, function attributes, or intrinsics. There are also toolchain conventions, which standardize the command line arguments of tools and compilers. And finally, there is the assembly manual, which defines and specifies the assembly language extensions. The RISC-V toolchain community interacts and overlaps with many other software communities. For example, there are a lot of open source software projects where the RISC-V toolchain community interacts with. For example, GNU binutils, GCC, llvm, glibc, QEMU, GDB, and Linux. In part 2, we will talk about RISC-V toolchains. We will go through the components of toolchains. We will have a look at different types of toolchains. We will go through the terminology, have a look at GNU toolchains and llvm, and we will talk about toolchain builders. Finally, we will talk about contributing to the individual toolchain projects and have a quick look at the compiler explorer. Let's talk about compilers. Compilers translate a program from one language to another one. For example, a C compiler compiles C code into some assembly language. Compilers, from a high-level view, consists of three parts. The language front end, which is parsing the source code. The middle end, which is transforming and optimizing the code. And the back end, which emits the target code. Famous OSS compilers are GCC and llvm. What we should note here is that toolchains are not identical to compilers. But typically a toolchain contains one or more compilers. So what are the components of a toolchain? Well, let's split them into two pieces. First of all, the host executables. For example, the compiler, which compiles a high-level language to assembly code. Then the assembler, which assembles the code to object files. There's also the linker, which binds multiple object files into a binary or library. And there are different other tools like object dump and the debugger. But a toolchain also contains target executables and libraries, including the loader or dynamic linker, the C or C++ runtimes or any other language runtimes, other support libraries like address sanitizer libraries or cryptographic libraries, and header files. Let's have a look at different toolchain types in the RISC-V ecosystem. I've picked two different examples which are very common. First of all, there is the ELF or bare metal toolchain. This toolchain targets embedded systems without feature-rich operating systems. Often, real-time operating systems with a specific purpose are used. They often focus on code size and use a C library that is also optimized for code size, just like Multilib or picolib-C. They're trading features for lower memory footprint. That means that features like dynamic linking is often not available. On the other hand, there are Linux toolchains, which target application development for Linux. Here, dynamic linking is a built-in feature. Additionally, these toolchains have a feature-rich C runtime environment. In most cases, this will be provided by glibc. And there are a lot of C extensions. For example, a lot of POSIX APIs are available. So now that we know different RISC-V toolchain types, let's have a look at cross-toolchains. When cross-compiling, we distinguish three different machine types. The build machine is the machine the toolchain is built on. The host machine is the machine the toolchain will later be used. And the target machine is the machine the toolchain generates code for. So for example, on an x86 machine, we can build a cross-compiler that will later be executed on an AH64 server to build RISC-V binaries. The description of the machines is done by machine triplets, which have the form machine, vendor, and OS. So for example, x86 unknown ELF, or RISC-V 64 unknown Linux GNU. There are different types of toolchains. A native toolchain would be if build, host and target machines are identical. A cross toolchain has build and host machine identical, but compiles code for a different target machine. A cross-native toolchain would be if the build machine would be different than the host, which would be the same like the target. So you basically compile a toolchain which can later be used as a native compiler. And finally, there is the Canadian cross toolchain, where build, host and target machine are different. Let's focus on cross toolchains. So for example, we have an x86 machine where we will build a cross toolchain that we will later use on exactly the same machine to build code for RISC-V 32 or RISC-V 64. When building such a toolchain, we can typically go through the following steps. First of all, we need to build the assembler and the linker. Both of them will be executed on the host machine, so on the x86 machine, but they will target the RISC-V specific code. Then we build a cross compiler, a limited cross compiler actually, which will also be executed on the host machine. With this cross compiler, we can build the C runtime. Once the C runtime is complete, we can build a complete cross compiler again, but this time we have a complete target C runtime available. Further, we can build also other language runtimes, for example, a C++ runtime. And in the end, we can also build additional libraries or tools, just like debuggers. Once we have a cross toolchain, we can build a native toolchain on top of that. For example, we can compile or cross-compile the assembler and linker, which can then be executed on the target machine. The same applies to the compiler and other tools. The C runtime for the native environment is actually the same like we have for the cross toolchain. Let's have a look at another term that is often used in the context of cross toolchains, the sysroot. So when looking again at the building steps of a cross toolchain, we can see that there are components that are linked on the host machine but never executed there. Instead, they are meant to be executed on a target machine. So these components are basically shared between the cross compiler on the host machine and the target system. Of course, besides the libraries, also the header files need to be shared. So the sysroot is the collection of header files and library files of the target machine, which are required for cross compilation on the host machine and required for native execution on the target machine. So let's get a bit more concrete and have a look at what the GNU toolchain consists of. So main building blocks are of course the GNU bin utils, which bring the assembler, GAS, the linker, LD or its alternative gold, the archiver, AR, various ELF tools like readelf, object dump, object copy and so on, other helper tools and the profiler gprof. It also includes the GNU compiler collection. In most cases this will be the C and C++ compiler, GCC and G++. Also the C++ standard library, libstandard C++ will be included. Another project that is part of the GNU toolchain is the GNU C library or glibc, which brings the C runtime library and the runtime linker. Finally, there is the GNU debugger. While this would be already enough to build a GNU toolchain, it's possible to add even more components. What could be done, for example, is that we add QEMU, which brings a system emulator and a user mode emulator. We can also include other parts of the GNU compiler collection, like the Fortran, Ada or Rust compiler, plus their runtimes. We could also include various cryptographic libraries. We could even include Unix utilities or interpreters for Perl, Bash, and so on. Eventually we will end up in building a complete Linux system. But the question is, of course, do we really want to do that? If that's intended, then we might better move to other projects like Buildroot, OpenWRT or Yocto. A software project which we haven't mentioned so far is llvm. Similar like GCC, llvm is a collection of compilers and toolchain elements which don't contain a C runtime library. So if we have already a GNU toolchain, we can see llvm as just another cross-compiler. So all we need to do is to build it and tell it where the sysroot can be found. llvm comes with its own set of tools and libraries. Famous ones are Clang, which is the C frontend, Flang, the Fortran frontend, and others. So after going through all these software projects, the big question is, how can we put this all together and build a RISC-V toolchain? There are two obvious ways. One is to build manually everything on the command line, and the other one is to use a toolchain builder. When deciding to build everything manually, the Linux from Scratch project is a very helpful resource. This project aims to build a complete Linux system on the command line and provides a lot of documentation around that. Among the initial steps, there is of course the instructions to build a cross toolchain. When we want to use a toolchain builder, maybe CrossTools-ng is the better solution. It focuses on building only toolchains, supports many targets, and also allows to build native tools. It also allows much flexibility of what the sysroot will include. Another project that is very famous among the RISC-V developers is the RISC-V GNU toolchain repository. It only builds the RISC-V GNU toolchain at the moment, plus QEMU. However, there is a pull request for llvm support. One of the big benefits of this project is that it allows to execute the GCC regression test suite using the built QEMU binary. Therefore, it is a good choice for the RISC-V toolchain development. If you're interested in toolchain development, there are multiple ways to contribute. All projects have issue trackers, where you can file an issue in case you see a missing feature or a bug. There are also mailing lists and forums for information exchange or discussing technical details. For submitting patches, all these projects have either mailing lists or other review systems. People are encouraged to review patches of others. A way to get an overview of submitted patches is Patchwork. I've listed here two different Patchwork instances that track all the patches which are submitted to different open source projects. An excellent resource that's often used by compiler developers is Compiler Explorer. The Compiler Explorer is an interactive online compiler which shows the assembly output of compiled C, C++, Rust, Go, or many other source codes. It supports a range of GCC and llvm releases, and of course it also supports building for RISC-V. Typical interesting use cases are comparing the generated code of different compiler versions, different backends, or compiling code with different flags, for example optimization levels or different extensions. In part 3, we will get our hands on the keyboard and build 3 different toolchains using the RISC-V GNU toolchain repository. So here's what we are going to do. The 3 toolchains which we are building are first a RISC-V 32-bit bare metal Multilib toolchain, then a 64-bit RISC-V Linux GNU toolchain, and finally a 64-bit RISC-V llvm toolchain. As toolchain generator, we will be using RISC-V GNU toolchain. As mentioned before, llvm toolchain support is only available in a pull request of this repository. You can find the link here. So let's quickly have a look at the project. So I've already opened the README of the RISC-V GNU toolchain repository. This README contains all the information which we need to know in order to build a RISC-V toolchain. At the beginning of this document, we have all the required packages listed, including the instructions how to install them. I've already done this, so we can simply skip over this section. But if you are about to build the first time, you probably want to make sure that all of these requirements are installed. In the next section, we already see how Multilib Toolchain or ELF toolchain is being built. All we need to do is invoke configure, specify where we want to install the cross toolchain, and invoke make. That's all we need. The defaults will set up everything to build a 64-bit toolchain, and that's all what we need. So let's have a look at the Linux toolchain. It's basically exactly the same, with one difference. Instead of make, we're calling make Linux. Again, the default will be a 64-bit target, but instead of newlib, we will use glibc in this case. If we want to build a Linux toolchain for a 32-bit target, we can use the configure arguments with arch and with ABI. There's also the option to build a Multilib toolchain, which brings toolchains for both 32 and 64-bit cross compilers. The next part is the test suite. Let's have a look at this a little bit closer. So GCC has built-in regression tests, and in order to build them or to execute them, we can use this RISC-V GNU toolchain repository. So what we need to do to run them for a Linux toolchain, we need to invoke make report Linux, specify the simulator which we are going to use. In this case it is QEMU, and then simply wait for the tests to be executed. Of course, there's also the possibility to restrict the number of tests which we are interested in. So for example, we can set the environment variable run test flags to RISC-V exp, with the effect that only RISC-V specific target tests will be executed. This will make the test cycles much faster. There's also the possibility to further restrict to specific patterns. So you have the test case directory for the RISC-V tests, and in this directory we can specify a pattern for the test cases that will be executed. we can skip the section about submodules because we will use out of tree sources, which are listed here at the bottom. So this repository allows to override all default sources which it points to. As already mentioned before, all sources which are external are referenced via Git submodules. By using these configure flags which are listed here, for example with GCC source, we can specify local directories on our machine where the sources we want to build for are located. This will speed up dramatically your build processes in case you already have a GCC source or any other source of these projects available. Okay, let's build our first toolchain. I've already prepared a directory where I have checked out a branch of the RISC-V GNU toolchain. So in order to build the toolchain, remember we wanted a 32-bit toolchain using Multilib as a C library, we can do the following. We need to configure, need to set the prefix, and in this case I want to explicitly set the arc and the ABI. This might already be picked up by the defaults, but in any way we can still set it explicitly as well. As mentioned before, I'm not interested in downloading all the sources again. Instead, what I want to do is I want to use the sources which I have already checked out locally. So what we can do is we can set with GCC source the source to a local checked out GCC sources. Let's do the same with bin utils as well. Same again with GDB. And finally the same with Multilib. And that's all. After we've configured everything, all we need to do is start the build process by typing make. I will do a parallel make since that will speed up the compilation significantly. After that, I will stop the video, wait until it's completed, and will continue with the video once the build has been completed. So as you can see, the build already succeeded. And as you can see, exit code is 0, so everything was clean, everything built. So what we are going to do now is, let's have a look what the toolchain actually can do, if it works. To do so, let's go into the directory. We have some sample code. Here we have a Hello World example. I think I don't need to explain this in detail. What we can do now is we can have a look at how we can build a binary using this new build toolchain. So what we are using is RV32 newlib bin RISC-V GCC. Let's optimize for size. And let's call the resulting binary Hello World. Okay, well, that succeeded. That's actually good. Let's have a look what file says to the generated file. As you can see, it's a 32-bit executable RISC-V, float ABI like we decided to build, and everything looks good. And given it's statically linked, well, we can even try to execute it. To do so, I have already installed bin format MISC locally on my machine, so that will most likely pick up the execution of this binary. Let's see if that works. And yes, here we have the Hello World string printed out. Okay, but let's look a little bit deeper and use the tools which we have just built using bin utils. So what we can do is we can use readelf, for example. Readelf, and let's have a look at the header. So, and you can see here we have the elf header with the magic. We have the class which is elf32, and everything looks good. One more thing that might be of interest is having a look at the disassembly. To do so, again, we will use a tool from bin utils, which is called object dump. -d for disassembly, hello world, and let's pipe it to less because that will flood our terminal otherwise. Yes, and here we can see the text section is already here, and here we even have in the middle of the screen the code of the main function. So you can see the jump and link instruction here, which is calling put s, so put string, and if we go through that, it actually looks quite sane and everything looks good. So it looks like our new toolchain, 32-bit toolchain, is actually working. So let's move on to the next toolchain. Okay, now we're ready for building the RISC-V 64-bit Linux toolchain, and I've already prepared the configure flag. Similar like before, I've set up a clean RISC-V GNU toolchain repository or directory. I will paste the configure flags here. So again, we have configure, we have the prefix, we explicitly set the arch and the ABI. So in this case, RV64GC, and the ABI is LP64 with hard float. The enable Linux flag here changes the default from newlib to Linux. So all we need to do later is to type make, and this will immediately build the Linux toolchain. So we don't need to follow this make Linux instruction here. And yeah, again, we set all the local sources so that the build process will be faster because we don't need to download all the repositories. Okay, let's see if it works. Yes, everything has been accepted. And now simply start the build process. Maybe one thing what we should mention here is we want to not only build the toolchain but also the simulator. So we will do a little bit more. I've prepared this as well. So we will do again a parallel build followed by a make build sim, so build simulator, and the simulator can be specified via environment variable, and in this case we want to build QEMU. So these two commands will be executed after each other, and again this will take quite some time. I will stop the video and jump in once this is completed. Okay, let's start it. Okay, so the build just succeeded. Let's have a look if it was successful. Yes, exit code is 0. That's a good sign. So in this case, we could also have a look at some small examples and see if the code which is generated is actually sane. Well, we can do that later. Before that, let's have a look at the test suite, and let's use the RISC-V GNU toolchain repository to execute all the RISC-V specific test cases in GCC. So I've prepared the command for that. So you remember we have built the toolchain and we have built the emulator QEMU, and what we are going to do now is we set the run test flags to risc5.exp, which is the overall file for all RISC-V specific tests. Then the normal make command, and we call the make target report. Additionally, we set the simulator explicitly again to QEMU. Well, and if we do that, you can already see the test suite is running, and well, it's already done. And when we look at the stats here, it was testing RV64GC with the ABI LP64D with the code model Medlow, and didn't find any errors at all. Well, that's actually a good sign. In this case, let's quickly move on and have a look if the toolchain can be used like we used before, or like we tested before the 32-bit toolchain. So let's invoke GCC with O3 hello world.c and build hello world like before. Let's have a look. What's the generated file? In this case, it's a 64-bit ELF file for RISC-V, and it's dynamically linked. So it's not statically linked like before, but we have an ELF interpreter, or LDSO, dynamic loader, which is explicitly named here. So if we want to execute that, we can actually use the build QEMU. So let's do that. Here you can see with tab completion what is included, which binaries are available. You can see address to line, AR, AS, C++, C++ field. So a lot of GCC and binutils tools. But at the top of the list, we have QEMU for 32-bit and 64-bit. Let's use the 64-bit QEMU and put as an argument our hello world binary. And let's see if that executes. Excellent. So QEMU was emulating a RISC-V 64-bit environment and could execute our hello world program. Let's do the following now. Let's have a look at the generated code again. Well, let's have a look at the headers first. Similar like before. The class is elf64 in this case, but there are no surprises here. And yes, let's have a look. into the binary. And you can see we already have a little bit different code here. We have a procedure linkage table. But again, the main is here. It calls puts again, but this time it's not an absolute address, but it's a symbol in the PLT. So compilation looks definitely a little bit different in case of Linux, but as you have seen before, everything was working fine. And yeah, we have a working Linux toolchain, which was tested, didn't show any regressions, and our build QEMU was able to execute the generated binaries. Well, with that said, let's have a look at llvm. So as mentioned before, the llvm support is not merged yet. We have a pull request for that, which can be found here in the pull requests. I've already checked out all these changes which are necessary here. I think what is important is that we have a look at how this can be used. So let's scroll down a bit. So here you have it documented. All we need to do is enable llvm. And currently it only supports Linux toolchains. But that's okay. So with that said, let's simply test this and build an llvm toolchain. I've already prepared the configure line again, like before. So what do we have here? Again, we set the prefix, we set explicitly the arch and the ABI, and we enable llvm and Linux. Additionally, we also specify the llvm sources besides all the other sources like we did before. So, and that's all we need. And the next step here will be make jnproc. And yeah, again, this will take quite some time, and I will stop the video and come back once it is completed. Okay, building the llvm toolchain succeeded. Yes, return code is 0. So what can we do now? We could have a look at the generated binaries of Clang. Let's delete the example from before and let's use the freshly built toolchain llvm bin. You can see there are a lot more different binaries in the bin directory, simply because all these llvm binaries are here now as well. What we are interested in is Clang. Let's use the instructions from this example here. Hello world, and let's build hello world.c. Okay, compiled. We didn't build an emulator here, but we could use the one which we built previously with the Linux toolchain. And let's have a look if the hello world application can be executed. Yes, works fine. But now we are interested, of course, in also building C++ code. To do so, let's hello world. Okay. Of course, that's the file name. Let's try to execute this again. It still works. What I haven't shown you yet was the sources, actually. Here we can see IO stream is included. Standard cout is used to print. So clearly C++ code. And well, everything worked as expected. And yeah, with that said, that's all from the toolchain side. In part 4, we will have a look how debugging works in an emulated RISC-V environment. Since we're focusing on debugging, let's assume that we already have a toolchain. And imagine that we observe some issue and we don't know exactly what is the cause of this issue. For example, the execution of a compiled application in QEMU aborts. So let's have a look at how QEMU's GDB support can be used for cross-debugging the application. I've listed the essential steps here, but let's go through that on the command line. Okay, let's have a look how debugging works in an emulated environment. We've built the toolchains in the hands-on sessions before, so we will simply reuse them. What we have here is a simple C file which eventually calls abort if the return value of a function of the printf function here is 13. And obviously this will be the case, so the abort will be triggered. So there will be no surprise, but let's see how much tool support we get to debug this. Okay, so first of all, what we need to do is we need to compile the whole thing. So we use GCC like before to build the hello world abort. And now what we can do is we can execute this binary and see what will happen. And hello world will be printed as we have seen in the source code, and immediately afterwards there will be an abort. So the question is, what can we do now? Obviously, just running GDB will not work because GDB doesn't know how to execute your binary. So what we need to do is we need to connect QEMU to GDB, and this can be done by simply stating the -g flag to the QEMU binary. So what we are doing here is we are calling QEMU RISC-V 64-g, then we set an arbitrary port, let's say 1234, and then we specify the binary. Once we do that, the terminal will be halted, so this will actually block and wait until somebody connects on port 1234. So we need a GDB instance that will connect there. And in order to make this a little bit smoother, I've already prepared a GDB init script. So that GDB init script executes target, remote, localhost. So it connects to the localhost on port 1234. That's exactly where our QEMU instance is waiting. Additionally, I've already set the TUI mode to enable, and I've changed the layout to assembly, that we can see the assembly output, and break main, the last instruction here, tells GDB to set the breakpoint at the beginning of the main function. Okay, and what we can do now is we can start GDB, give it the ELF file, so it can extract meta information and help us to navigate through the code. And once GDB is started, it will look up in a couple of search paths for a GDB init file, and of course it will also look in the local file. There might be some security restrictions. It tells you what needs to be done in this case, but everything should be straightforward, so no complications here. And if we do all that, the GDB init script will be executed. It will connect to the QEMU instance, and here's what we get. You can see the application stands at _start, so that's the beginning of the execution. There's a lot of things that's going on before main is being called. It is possible to debug this here as well. I've done this in the past multiple times. That works perfectly fine. But in this case, we already set the breakpoint to main. So all we need to do here is, it wants to tell us more. So Q here. And now we simply say C for continue. And it executes everything up to main, where we have set our breakpoint. Here we can have a look at what's going on. So it is about to call printf in the statement below that highlighted line. So below, the next instruction would be load immediate 13, and then we have branch equal to main plus 28, which would be the abort statement. So if the return value A0 is not 13, then A0 will be loaded with 0, load immediate 0, and we will eventually return from main, and everything will be fine. So let's see what happens at runtime. What we can do now is we can use step I to step into the next instruction, even if it's a call, we follow here. But honestly, we are probably not interested in looking into the execution of printf. So simply finalize this. Here we can now list the register values. So IR was the command, and here we can already see A0 has the value 13. That's the A0, as you know from the calling convention, is the return register, the return value, and we can already see what will happen in this branch condition. But let's use step I to move forward once again, and here we can already see now it's about to jump and link to abort, where it will not return anymore. So this demo showed you already how you can connect QEMU with GDB for a foreign architecture using a cross toolchain. And with that said, that's all. Thanks. We are now at the end of the tutorial. Let's quickly recap what we've learned so far and have a quick look at the references for further information. Let's quickly recap the contents of this tutorial. We heard about RISC-V and RISC-V International, the groups, Nonizer Extensions, the SIG toolchain, the PSABI, and other convention documents. We also heard about RISC-V toolchains, their components, what a sysroot is, and how to contribute to them. We also had some hands-on session where we were building our own RISC-V toolchain using the RISC-V GNU toolchain repository. The second hands-on session was about debugging in an emulated environment using QEMU and GDB. And here on the last slide, you can find a couple of references and points of contact where you can get further information. With that said, thank you very much for your attention. and please let me know if you have any questions.